The answer is more similar than you should be. When population geneticists began mapping human genetic diversity in the 1980s and 1990s, they expected to find what you would expect to find in a species of our size and our age and our geographic distribution. Homo sapiens has been around for at least 300,000 years. We have spread across every continent on Earth. We number in the billions. By every standard measure of population biology, a species with that history and that range should carry within it a deep reservoir of genetic variation, the accumulated differences of hundreds of thousands of years of separate populations evolving in separate environments. What they found instead was a reservoir that was, by those same standards, strikingly shallow. Human genetic diversity is low, not slightly low, measurably, significantly, surprisingly low in ways that do not match the size and age and distribution of our species. A single troop of chimpanzees living in a forest in West Africa carries more genetic variation within its members than the entire human population of the planet. Two chimpanzees chosen at random from the same forest are, at the level of the genome, more different from each other than two humans chosen at random from opposite sides of the Earth. This is not a minor statistical curiosity. It is a signal, and the question it raises is one that population genetics, once it had the tools to ask it properly, could not ignore. Something happened to us. At some point in our past, the human population was reduced so severely, and the reduction was maintained long enough, that the genetic diversity of our entire species was compressed into whatever variation existed within a small surviving group. Scientists call this a population bottleneck. The word is clinical and contained, the kind of term that sits comfortably in a journal and less comfortably in the imagination. What it actually describes is this: every person alive today, every human being who has drawn breath since that event, is descended from a group of survivors so small that their numbers would not fill a large sports stadium, possibly far fewer than that. The strangers you will never meet, living in cities whose names you may not know, speaking languages you cannot pass, are not merely your fellow humans in some abstract sense. They are, in a genealogical sense, more literal than most people are comfortable sitting with, your relatives. The genetic distance between any two humans chosen at random from anywhere on Earth is smaller than the genetic distance between two chimpanzees from the same forest. We are one very large family that has forgotten it is a family. Something made us that way, and for a long time, no one knew what it was. The answer, when researchers began to piece it together in the 1990s, pointed toward a place that most people outside of Indonesia had never heard of. A lake in the highlands of northern Sumatra, a body of water roughly 100 kilometers long and 30 kilometers wide, ringed by steep green hills and fed by rivers that carry the color of the surrounding forest into water, so clear that on a calm morning you can see the bottom 60 feet down. The lake is called Toba. It is, by any reasonable measure, beautiful. It is also, by any reasonable measure of geological violence, one of the most consequential places on the surface of this planet. What lies beneath that water, and beneath those hills, and beneath the landscape for hundreds of kilometers in every direction, is the remnant of the largest volcanic eruption in the last 2 million years of Earth history. An event so large that the numbers used to describe it require translation before they mean anything to a human mind. An event whose relationship to the genetic signal described above is one of the most actively debated questions in the study of human prehistory. That last sentence matters. It needs to sit for a moment before we go further. The volcanic eruption is not in dispute. The genetic signal of unusually low diversity in our species is not in dispute. what remains an open and genuinely contested question among researchers, argued in journals and at conferences, and in the careful, specific disagreements that science runs on, is the exact nature of the relationship between those two facts. Whether the eruption caused the bottleneck, whether it deepened one that was already underway, whether the connection is as direct as it first appeared, or more complicated, or some combination of both. This is not a story with a closed case at the end. It is a story with a body of evidence, a set of competing interpretations, and a question that is still being worked on by people whose job it is to work on exactly this kind of question. What it is, beyond all of that, is a story about survival, about who survives when the conditions for survival are pushed past any threshold that evolution could have prepared a species for, about what kinds of creatures and what kinds of relationships between creatures prove durable when everything else is failing, and about what that durability might have left behind in the people who came after. To tell that story properly, we need to begin approximately 74,000 years ago, on the eastern coast of what is now the African continent, where a group of people is going about the ordinary business of an ordinary morning. They are a reconstruction. Let that be said clearly, because honesty about this matters for everything that follows. We do not know their names. We do not know their faces. We cannot recover the specific details of their individual lives, because they lived before anything existed that could preserve such things. What we can do is build them from the evidence that archaeology and genetics and geology together make available, filling in what the data allows and acknowledging, with care, the distance between what we know and what we are imagining. What the evidence allows us to say about them is this: they were fully human, not a prototype of human, not a simpler version of human, not a draft of the thing we eventually became. They thought in symbols. They communicated in ways complex enough to describe things that were not immediately present. They made tools that required planning across time to produce. They maintained relationships that lasted longer than a season. They had a relationship with their dead that suggests they understood, in some form, what death meant. They were people. And on a morning, approximately 74,000 years ago, they were living in a world that was, for a few more years, entirely intact. To understand what was about to be tested, you need to understand what it actually was. Not as a list of species names and geological periods and dates arranged in chronological order. Not the way a textbook handles the deep past. As a series of facts to be absorbed and moved past. What it actually was. The texture of it. The specific and unrepeatable character of a world that had been building itself, layer by layer and generation by generation, for longer than the human mind is genuinely equipped to process. Start with the planet, because the planet determines everything else. 74,000 years ago, Earth was in the middle of a glacial period, not the glacial period of popular imagination. A world buried uniformly under white and frozen into stillness. The reality was more complicated and, in its own way, more interesting than that. The ice was real. It was vast, covering much of the northern hemisphere in sheets that in some places reached thicknesses measured in kilometers. But the tropics and subtropics were not buried under ice. They were compressed. The climate zones that today spread in a wide band around the equator were squeezed toward lower latitudes, pushed together, their boundaries shifting with the slow rhythms of orbital cycles that no living creature could perceive directly, but that shaped everything about where life could thrive and where it could not. Africa, in this period, was not a single climate. It never has been. It was a mosaic of environments, a patchwork of forests and grasslands and river systems and coastal zones, each shaped by local geography and the larger patterns of a glacial climate pressing down from the north. The eastern coast of Africa, where this story begins, sat within a region of particular biological richness, a place where the cold Benguela current and the warm Agulhas current met and mixed offshore, and where the result of that mixing was a coastal environment of extraordinary productivity. And then there was the coastline itself. During a glacial period, sea levels are lower than they are today. The water that in our time fills the ocean basins was 74,000 years ago, locked in ice sheets on land. Global sea level was somewhere in the range of 60 to 80 meters below its current position. What that means for the eastern and southern coasts of Africa is that the continental shelf, which today lies submerged beneath shallow ocean water, was then exposed as dry land. The coastline was farther out. The area of coastal habitat, the tidal zones and estuaries and rocky shores and shallow marine environments where the sea meets the land and the productivity of both is multiplied, was significantly larger than it is today. This mattered. It would matter more than anyone alive at the time could have known. Now, look at the people living along that coast. Homo sapiens was not the only human species on Earth 74,000 years ago. This is not a detail. It reshapes the entire context of the story. Across Europe and much of Western Asia, Neanderthals were established as the dominant human lineage. They had been there for hundreds of thousands of years, long enough to have developed their own adaptations to the cold landscapes of the north, their own tools, their own social structures. The older reconstructions of Neanderthals as dim and stooped and barely competent are not supported by the evidence. They buried their dead. They used pigment. They manufactured adhesives that required multi-step processing. They cared for members of their groups who were injured or elderly in ways that could not have survived without deliberate support from others. By any honest reckoning, they were cognitively capable beings with complex social lives. Across parts of Asia, the situation was even more complicated. Populations of archaic humans, whose exact nature is still being worked out from fragmentary fossil and genetic evidence, occupied regions that Homo sapiens had not yet reached in significant numbers. On the island of Flores, a small-bodied human population, which researchers call Homo floresiensis, appears to have survived in isolation and to have been capable of behaviors that required considerable cognitive sophistication. The world, in other words, did not yet belong to us. It was shared, in a complicated and probably not always peaceful way, among multiple human lineages with different histories and different strengths. What distinguished Homo sapiens in this period was not dominance, something more like a particular quality of restlessness, combined with a particular quality of flexibility, a capacity to inhabit a wider range of environments than any previous human lineage and to modify behavior in response to changed conditions more rapidly than the fossil record suggests other lineages could manage. The evidence for this comes from places that, by the standard of anything that happens later in human history, are unremarkable. Rock shelters and cave floors and open sites along the southern African coast where, layer by layer, researchers have uncovered a record of human behavior that is, when you look at it carefully, genuinely surprising for its time. Blombus Cave, on the southern coast of what is now South Africa, has produced ochre, the iron oxide pigment that humans were grinding and mixing and applying to surfaces, in quantities and with a consistency of technique that suggests symbolic behavior Not pigment used incidentally. Pigment used deliberately, repeatedly, in ways that imply a concept of meaning beyond pure function. The same site has produced perforated shells, small enough to have been threaded onto something, worn as ornament or as marker of identity or as signal of affiliation with a group. It has produced pieces of ochre engraved with geometric patterns, too regular and too deliberate to be accidental, too abstract to be simple representation. Someone made those marks. They knew what they were making. They expected the marks to mean something to someone. And then there is the evidence that, in some ways, says more than any of this. Materials that exist only in specific geological locations appear at these coastal sites in forms that required they be transported. Stone types available only from sources dozens or hundreds of kilometers away show up in tool assemblages at sites nowhere near those sources. This means they were carried. It means someone knew where to find them. It means information about sources, about routes, about the locations of specific resources, was being shared across distances too large for any individual group to cover through its own ranging. A network existed, not a network in the modern sense of something formal and maintained by infrastructure, a network in the most fundamental sense, a web of relationships between groups that allowed information and materials to move across distances larger than any single group could span. A network that functioned because people maintained it, visited it, reciprocated within it, treated the relationships it represented as worth the cost of sustaining. This is the most important thing about the humans living along the southern and eastern African coast in the period before Toba. Not any individual capability, not any specific tool type or behavioral innovation. The network. Because a network is not just a social convenience. In the context of a world where the environment can shift unexpectedly, where a drought can exhaust local food sources, where a group, reduced by illness or accident, may not have enough adults to function, a network is a survival resource of the first order. A connection to a group 50 kilometers away that knows where water persists through a dry season you have not experienced before. Access to materials that your local environment does not provide. The option of merging with another group when yours has become too small. The flow of genetic diversity that comes from intermarriage between groups that maintain contact over generations. These things have no weight and take no space and leave no obvious trace in the archaeological record. But they may have mattered more than any physical object that does leave a trace. The woman who anchors our reconstruction of this world was embedded in exactly this kind of network. We do not know the specifics of her relationships or the geography of her group's range. We know, from the pattern of evidence at sites of this period, that groups like hers maintained connections across distances. We know they exchanged materials. We know they shared information in forms that required language capable of describing things not immediately present, things remembered from the past or anticipated in the future. She was not surviving alone. She was surviving as a node in something larger than herself, something that had been built up over generations and that she was simultaneously maintaining without knowing it, depending on in ways that would become apparent only when it was tested. Now shift perspective. Shift it entirely. 10,000 kilometers to the northeast, in the highlands of what is now the northern part of the Indonesian island of Sumatra. Something had been underway for a very long time, long enough that no human mind, encountering the landscape above it, could have detected any sign of it, long enough that the concept of warning had no application. Toba is not a volcano in the sense that the word volcano typically carries. It does not rise from the landscape in a recognizable cone. It does not announce itself with a summit or a crater. visible from a distance. It looks, from above, like a lake. A large, beautiful, calm lake, surrounded by green hills and fed by rivers and occupied by fish and by the birds that eat them. What it is, beneath the surface, is a supervolcano. The distinction is not merely one of scale, though the scale is itself barely graspable. A supervolcano is a specific geological structure, a massive magma chamber that has been filling, incrementally, over hundreds of thousands of years, accumulating material faster than it can release it through ordinary volcanic activity. There is no gentle bleed of lava down a slope. There is no series of moderate eruptions distributing the energy incrementally. There is only accumulation, patient and enormous and completely invisible from the surface, until the pressure in the chamber finally exceeds the strength of the rock above it. At that point, what happens is not an explosion upward in the conventional sense. It is a collapse. The chamber empties faster than the rock above can adjust to the withdrawal of support below it. The roof fails. The landscape above falls inward, and everything that was in the chamber, and everything in the crust above it, is ejected simultaneously, not from a single vent, but from the entire rim of the collapsing caldera, a ring of simultaneous eruption points along a fracture system that may span dozens of kilometers. Toba had done this before, 3 times in the record that geologists have been able to reconstruct. Toba produced caldera-forming eruptions of significant scale. The deposits from those previous eruptions exist in the geological archive of South Asia. Thin white layers of ash in sediments that would otherwise show no sign of volcanic origin. Silent records of events that reshaped regional climates for years at a time. Each previous eruption had been large. What was coming was different. The magma chamber had been refilling since the last major event. It had been filling for a very long time. The pressure that had been building in the dark below the green hills of northern Sumatra represented an accumulation of geological force that had no equivalent in the recent history of the planet. The estimated volume of material that the eruption would eventually produce, approximately 2,800 cubic kilometers. To translate that into something the imagination can work, with the eruption of Mount St. Helens in 1980, an event that reshaped the landscape of the American Pacific Northwest and deposited ash across 11 states. Ejected approximately 1 cubic kilometer of material. Toba would eject approximately 2,800 times that volume. The largest eruption in the past 2 million years. Possibly the largest in much longer than that. And on the morning that our reconstruction of a woman and her group was going about ordinary life on the eastern coast of Africa, none of this was visible. None of it was detectable. The ground in Sumatra was doing what ground does when pressure has been building in a chamber below it for long enough. It was showing signs, subtle and ambiguous and entirely uninterpretable to any creature that had never needed to interpret them. The animals near Toba were already beginning to respond. The way animals respond to things they sense but cannot name. Moving in directions that had no obvious explanation. Behaving in ways that differed from their established patterns, in ways that no observer, had there been an observer, would have been equipped to understand. The world on that morning was still the world it had always been. Fully realized. Deeply complex, built over millions of years of evolutionary and geological and ecological process into something of extraordinary richness. It did not know it was living its final ordinary days. Nothing ever does. Beneath the green hills of northern Sumatra, something that had been accumulating for 200,000 years was almost finished accumulating. The world on the surface above it was still going about its business, entirely unaware that the business of the world was about to change in ways that would take tens of thousands of years to fully understand. The pressure in the dark below had no interest in what the surface knew or did not know. It had only the one thing that geological force has always had: the patient, indifferent certainty of physics working toward its conclusion. The animals knew first. This is not a metaphor. It is a biological fact about how certain species process low-frequency vibration and infrasound and the subtle changes in ground pressure that precede large seismic events. Elephants, certain species of birds, fish sensitive to changes in water pressure from below. In the days and weeks before the caldera collapsed, the highlands of Sumatra and the surrounding region were showing signs that no human of that era had the framework to interpret, but that the animals around them were reading with an urgency that had no name, because nothing that had a name had ever needed to name it. They were moving, not in the patterns of seasonal migration or the daily rhythms of feeding and rest, moving away from something, moving toward distances that put geography between them, and a source of wrongness they could detect and could not explain and would not survive regardless. The people living closest to the lake that would one day be called Toba had no equivalent warning system. They had senses calibrated by millions of years of evolution to detect the kinds of threats that the landscape of their experience had produced, the kinds of threats that could be seen, or heard, or smelled, or outrun. What was building beneath their feet was none of those things. It was pressure. It was physics. It was the final accounting of 200,000 years of geological accumulation, and it was about to present its bill. The sequence that follows is reconstructed from multiple lines of evidence: the chemistry of ash deposits found across South Asia and in ocean sediment cores, the pattern of collapse preserved in the present-day geography of northern Sumatra, the shape of the caldera, the distribution of the surrounding hills, the depth of the lake that now fills what was once solid ground, climate proxies in ice cores from Greenland and Antarctica that record the atmospheric consequences of large volcanic events. What follows is built from that evidence, held at the distance that honesty requires, and represents the best current understanding of what happened and in what order. The ground shook first, not with the sharp, directional violence of a fault line earthquake, with something more diffuse and more prolonged, the kind of shaking that comes from a magma chamber that is no longer able to maintain the structural fiction that the rock above it is supported. The fiction had been maintained for a very long time. It was ending now. The collapse, when it came, was not an explosion in the conventional sense. This distinction matters for understanding the geometry of what followed. When the chamber roof failed, it did not fail at a single point and push material upward through a vent the way a conventional volcanic eruption works. It failed across a zone measuring tens of kilometers in width. As the pressure below exceeded the tensile strength of the rock above, simultaneously, along the entire fracture system of the caldera rim, the landscape above did not blow outward. It fell inward, and as it fell, the magma below, under a pressure that had been accumulating for 200,000 years, erupted through every failure point at once. The eruption column that rose above the collapsing caldera reached, according to the best available estimates, somewhere between 40 and 50 kilometers in height. To translate that into something the imagination can locate, the layer of the atmosphere where weather occurs, where clouds form and rain falls and wind moves, in the patterns that determine climate, extends to roughly 15 to 17 kilometers above the surface in the tropics. The eruption column of Toba reached 3 times that height. It punched through the stratosphere and deposited its material directly into the layer of the atmosphere, where the global circulation patterns of high-altitude winds move without the friction of weather below them. Where particles, once injected, can be carried around the entire planet and can remain suspended for years. The volume of material ejected is estimated at approximately 2,800 cubic kilometers. Some researchers place the estimate somewhat lower. Some place it higher. The uncertainty in these estimates reflects the genuine difficulty of reconstructing the output of an event that occurred 74,000 years ago from deposits that have been partially eroded and reworked by subsequent geological processes. What is not in serious dispute is the order of magnitude. This was the largest volcanic eruption in the last 2 million years of Earth history. The imprecision in the exact numbers does not change that. For the people and animals in the immediate region of Sumatra, the question of survival was resolved within hours. The pyroclastic flows, dense currents of superheated gas and volcanic material moving outward from the collapsing caldera at speeds and temperatures that left nothing intact in their path, extended across the landscape of Sumatra and the surrounding area. The ashfall in the immediate zone was not measured in centimeters. In the areas closest to the caldera, it was measured in meters. There was no survival in the immediate zone. There was only the physics of what happens when material at those temperatures moves through a landscape at those velocities. But this is not primarily a story about Sumatra. Sumatra was the source. The story is about what the source sent outward, invisibly and without any mechanism that any living creature could detect or respond to, across an entire planet. And that story moves not at the speed of pyroclastic flow, but at the speed of wind and at the pace of seasons, operating through mechanisms that take days and weeks and months to deliver their consequences to places 10,000 kilometers away. The ash cloud that rose from the collapsing caldera was distributed by the prevailing wind patterns of the upper atmosphere across South Asia and the Indian Ocean region. Deposits from the Toba Eruption have been found in sediment cores from the Arabian Sea and the Bay of Bengal. They have been identified in archaeological sites across southern India, where researchers have found the distinctive white layer of Toba ash sitting between layers of human occupation. In some parts of South Asia, the ash deposit left by the eruption reached thicknesses of several meters. In others, it was thinner, distributed unevenly by the patterns of wind and atmospheric circulation that governed where the material settled. The immediate effects of this ashfall struck systems of South Asia were severe. Vegetation buried under ash does not recover quickly. Water sources, contaminated by volcanic material, become unusable. The food webs built on the productivity of terrestrial plant communities collapse when those communities are removed, and they collapse in a sequence. From the plants upward through the herbivores that depend on plants and the predators that depend on herbivores, that plays out over months rather than days. But the ashfall was not the mechanism that would define the next several years for the rest of the planet. The mechanism that would do that was rising into the stratosphere with the eruption column, invisible and odorless and undetectable by any sense that any creature possessed, and it was sulfur. The rock beneath the highlands of Sumatra is not ordinary crust. It is rich in sulfur-bearing minerals, the accumulated deposit of hundreds of millions of years of geological process in a region of complex tectonic history. When the magma chamber erupted, it did not simply produce a cloud of generic rock vapor. It produced a cloud that carried an extraordinary quantity of sulfur dioxide into the upper atmosphere. Sulfur dioxide that, once in the stratosphere, undergoes a chemical conversion into sulfuric acid aerosols, microscopic droplets of acid suspended in the high-altitude air. These aerosols have a property that makes them, in the context of the effects of large volcanic eruptions on global climate, more consequential than the ash itself. Ash settles. It is heavy enough that, over months, it falls back to the surface. Sulfuric acid aerosols, small enough to remain suspended by the dynamics of the stratosphere, do not settle on the same timescale. They persist. And while they persist, they do something to the light from the sun that has consequences for every organism on Earth that depends on that light. They reflect it. Not all of it. A fraction. The exact fraction depends on the density of the aerosol layer, which depends on the quantity of sulfur injected, which in the case of Toba was very large. The estimates of how much cooling the Toba aerosols produced at the surface vary among researchers and among the models used to calculate them. Some estimates suggest a global average surface temperature reduction in the range of 3 to 5 degrees Celsius. Some models suggest the reduction may have been larger in certain regions, smaller in others. The duration of the cooling effect is also debated. Years. Certainly. Some researchers argue for a decade or more in terms of significant impact on surface temperature. The uncertainty in these numbers is real and should be acknowledged. Climate modeling of events that occurred 74,000 years ago, using proxies from ice cores and ocean sediments and pollen records rather than direct measurement, involves assumptions and limitations that the researchers who do this work are careful to be clear about. What is not uncertain is the direction of the effect. The stratospheric aerosols reflected incoming solar radiation. The surface of the planet received less energy from the sun. Temperatures fell. The degree and duration are debated. The fact of cooling is not. In southern Africa, 10,000 kilometers from the collapsing caldera, the woman we have been following did not see an eruption. She did not hear a shockwave. She did not watch ash fall from a darkening sky. What reached her in the weeks and months that followed an event on the other side of the Indian Ocean was something that had no form she could see or touch or name. The light was a little less than it had been. Not darkness, not night in the middle of the day, just a quality of the light that was slightly different from what it had always been. A reduction in the intensity of the sun that was too small to name on any given day and too consistent to ignore across a season. The warmth that the midday sun had always delivered was delivering something slightly less than what it had always delivered. And the things that depended on that warmth, the plants and the insects and the fish in the tidal pools and the animals that ate the plants and the insects and the fish, were beginning to respond to the difference. She could not have known what was causing this. She could not have known that a mountain 10,000 kilometers away had broken open and sent a layer of acid into the sky above her. She had no framework for that knowledge and no way to obtain it. She only knew that the world around her was beginning to feel, in ways too subtle and too consistent to dismiss, slightly different from what it had always been. That slight difference was about to become something else entirely. The first year after the eruption was hard in the way that hard years had always been hard. This is the most important thing to understand about the beginning of what followed, because it is the thing that made the long dark different from any other catastrophe in the range of human experience. There was no moment when everything changed. There was no day when the sky went dark and stayed dark, and the animals all died, and the world declared itself to be in a new and terrible condition. There was only the slow accumulation of slightly less, repeated across seasons, each iteration indistinguishable from ordinary difficulty, and the whole of them together amounting to something that had no precedent. The rains came a little later than they usually came. The plants produced a little less than they usually produced. The animals were a little harder to find than they usually were. The shellfish in the tidal pools, which had been a reliable source of protein through previous difficult seasons, were a little less abundant than they had been the season before. A little, and then a little more. The group moved more than they had before. Movement was the foundational strategy of hunter-gatherer survival, the first and most basic response to resource scarcity. You moved toward food. You moved toward water. You moved toward the territories of neighboring groups. If those groups were part of your network, and the network was functioning, and you drew on the relationships you had maintained across seasons of plenty to sustain you through seasons that were not. The woman knew how to read the landscape for signs of what it could provide. She had been learning this her whole life, from the older members of her group who had been learning it their whole lives. Layered knowledge, accumulated across generations, and stored not in any object, but in people. Where water persisted through dry seasons that came earlier than expected. Which plant species were reliable when others failed? Which sections of coastline produced shellfish in sufficient quantities when the inland food sources contracted? She used what she knew. The group survived the first year. The second year was harder. The volcanic aerosols in the stratosphere were still present, still filtering the sunlight by a fraction that was invisible to the eye and measurable in its effects on everything that photosynthesis drove. Plants, calibrated by millions of years of natural selection to the specific light conditions of their environment, do not simply perform at reduced efficiency when those conditions shift. Some do not flower in the season when they would normally flower. Some do not set seed in the quantities they would normally set seed. The forest edge, which had been a zone of particular productivity, where the resources of woodland and open ground overlapped, was contracting. Not dramatically, not in a way that any individual day announced as significant. But over 2 years, the zone was smaller, and what it produced was thinner. The group was making the same decisions they had always made, using the same knowledge they had always used, and getting less in return than they had always gotten. The arithmetic of survival was shifting in one direction, and it was not a direction that offered any obvious response. And then something happened in the second year that complicated the picture in a way that, looking back across 74,000 years, seems like the most important fact of this entire period. Not everyone was failing equally. The groups living closest to the coast, the groups with reliable access to the tidal zones and the marine resources of the continental shelf, were experiencing a different version of the long dark than the groups living inland. The ocean does not respond to reduced sunlight the way terrestrial ecosystems respond. The marine food chains that begin with phytoplankton and move upward through shellfish and fish and marine mammals are affected by the same reduction in solar energy that affects land plants. But the ocean's thermal mass means the response is slower, the change less abrupt, the collapse less immediate. The shellfish were still there, fewer than before, in some locations, but there. The fish in the shallow waters of the expanded continental shelf were still there. The birds that nested along the coast were still there. For a group with the skills and knowledge to exploit these resources, the coast was not the world it had been before the eruption, but it was a world that could still support life at levels that the degraded inland environments increasingly could not. This is not a minor detail. It is. Based on the archaeological evidence that has been recovered from this period, one of the most consequential geographical facts in the entire history of our species. The coast was a refuge. Not in the sense of a place of safety where nothing was wrong. Things were wrong there too. The wrong light, the wrong temperatures, the acid rainfall that reached even the coast and stressed the vegetation of the shoreline. But wrong in a way that was survivable, in ways that the wrong of the inland environments, for groups without the specific knowledge and skills to exploit marine resources, was not. The groups that had built their survival strategy around the coast, that had accumulated across generations the detailed, specific, hard-won knowledge of how tidal zones work and when shellfish are safe to eat and where fish concentrate in different seasons. These groups had, entirely by accident of geography and prior investment in knowledge, found themselves in the one category of environment on a damaged planet that was still producing enough to sustain human life. They had not planned for this. No one had planned for anything. The coast had been rich before the eruption, and it remained, relatively, less poor after it. The groups were there because they had always been there, because their parents had been there, and their parents before them, because the knowledge of how to live on the coast had been transmitted across enough generations to become the foundation of their survival strategy. The accident of where you were was, in those years, the most important fact about you. But the story does not end with coastal groups surviving and inland groups failing, because the landscape was more varied than that binary allows, and because the network that connected groups across distances was not simply switched off by the eruption. It was stressed, and what it did under that stress tells you something important about what networks made of people do when they are pushed past their comfortable operating conditions. They shrank. Not overnight, not in a single season when every connection was severed and every group was suddenly alone. They shrank gradually. As the carrying capacity of the landscape contracted and the distances over which groups could range while still returning to their home territory became shorter, and the groups that had been at the edges of the network, the ones whose connections required the longest maintenance, began to drop out of contact, not because they chose to, because the cost of maintaining contact in the currency of time and energy and food that maintaining contact requires had risen past what a group running on deficit could pay. A network that runs on surplus does not function the same way when everyone in it is running on deficit. Information stopped moving as freely. The knowledge of where conditions were better, of which routes were still passable, of which groups still had something to share, became harder to access precisely when it was most needed. The most valuable resource in a world where the environment was failing unevenly was information about where it was failing less, and the mechanism for distributing that information, the network, was itself a casualty of the conditions that made the information so valuable. The third and fourth years brought something that the first 2 years had not prepared them for, though no preparation would have been adequate. The network that had sustained the woman's group was not gone. It was not gone in the way that a fire goes out or a river runs dry. It was gone in the way that a web goes when too many of its anchor points have failed. Not from any single catastrophe, but from the cumulative weight of too many small failures across too long a time. The connections that remained were the ones to the nearest groups, the ones whose territories overlapped enough that contact could be maintained without the investment that longer-range connections required. The connections to groups farther away, the ones that had provided access to materials and information that no single territory could supply. Those had frayed, and in many cases had not survived the third year. Knowledge was dying with people. This is the part of the long dark that the archaeological record cannot capture directly, but that the structure of what was happening makes inevitable. The knowledge that the older members of any group carried, accumulated across decades of living in a specific landscape and learning its patterns and its exceptions and its hidden reliabilities. existed only in those people. When a person died, that knowledge died unless it had been transmitted. Transmission requires time, and conditions stable enough for teaching to occur, and the presence of younger people in sufficient numbers to receive what was being taught. The conditions were not stable. Time was not available in the quantities that transmission requires. The older members of groups were dying at rates that the compounding stresses of chronic scarcity produced in people whose bodies were working harder than their food supply could support. And the knowledge they carried, the precise and detailed and irreplaceable knowledge of how to live in a specific landscape through conditions that no one had experienced before, was going with them. The woman understood. In the way that people understand things they have never needed to articulate, because the understanding has always been obvious. That the older people in her group were the most important people in it, not because of their strength, which was diminishing, because of what they knew, because of the decades of accumulated observations stored in them that could not be recreated from scratch, only transmitted, and only transmitted to people present enough and stable enough and fed enough to receive it. She was trying to be present. She was trying to keep the people who carried the knowledge fed and alive long enough to give her and the others around her what was in them. She was not always succeeding. By the end of the 4th year, the group was smaller than it had been at the beginning of the first. Not dramatically smaller. Not in the way that a catastrophe produces sudden reduction. Smaller in the way that chronic attrition produces reduction. One person at a time. Each loss specific and individual and mourned in whatever way mourning expressed itself in that time and place. And the cumulative total of those individual losses amounting to a group that was now operating with fewer hands and less knowledge and less margin for the errors that reduced margin inevitably produces. The 5th and 6th years are where the evidence becomes most interesting and most contested. Because something was happening that was not uniform across the range of human habitation in Africa and beyond. The groups that had found the coast and had the knowledge to survive there were not thriving, but they were continuing. The groups that had access to river systems that maintained water through the extended dry periods that the cooler, drier climate was producing were finding resources that groups in the degraded middle ground between coast and permanent water were not finding. The extinction of the human population, if extinction was what was happening, was not happening everywhere at once. It was happening in a pattern, and the pattern had a logic. And the logic was the same logic that had always governed survival: what you knew, who you knew, and where you were. The long dark was lifting. By the 6th year, in the way that the effects of large volcanic eruptions lift, which is to say slowly and unevenly and without any announcement, the aerosol layer in the stratosphere was thinning as the chemical processes that remove it gradually reduced its density. The light reaching the surface was incrementally improving. The temperatures were incrementally rising back toward what they had been before the eruption. But the world that the improving conditions were returning to was not the world that had existed before. The ecosystems that had been disrupted did not reassemble themselves in the same configuration. Species that had been locally abundant were locally gone in some areas. Their populations reduced below the threshold at which recovery was possible without recolonization from elsewhere. Plant communities that had defined the character of specific landscapes had retreated to refugia from which their recolonization would take not years, but decades. And the human groups that had survived the long dark were in different places than they had been before it began. Smaller, more concentrated in the environments that had proved survivable, more dependent on fewer connections, carrying less knowledge than they had carried when the dark began. Because some of what they had known had gone with the people who had known it. How many were left? This is the question that the long dark delivers to the doorstep of science. It is the question that the genome has been trying to answer since researchers first noticed that our genetic diversity was lower than it should be. And it is the question we turn to next. Because the answer, or rather, the honest account of how difficult the answer is to find, is one of the most important things about this story. Before we get there, sit with the long dark for one more moment. Not as a historical event at a safe remove, as someone's life, as the life of people who had names for each other and histories with each other and futures they were trying to build in the only way available to them, which was one season at a time. With the tools and the knowledge and the relationships they had and the capacity to adapt that their lineage had been building for a very long time. The woman from the coast did not know she was a character in the story of human survival. She did not know that the genome of everyone alive 74,000 years later would carry the signature of what she and the people around her were going through. She knew that the shellfish were fewer than they had been. She knew that two of the people who had known things she did not know were gone. She knew that the sky was still the wrong color in ways she could not name, and that the rains were still arriving late in ways she could not explain. She knew that morning came again, and that was enough to work with. That is what surviving the unsurvivable looks like from the inside. It looks like continuing, because continuing is what is available. She did not know how many others were doing the same thing in the darkness beyond her horizon. She did not know if there were thousands of them, each making their own small choices in their own damaged piece of the world. She did not know if there were hundreds. She did not know if the number was smaller than anyone. Looking back across 74,000 years, with the tools of modern genetics and archaeology and climate science, would find comfortable to contemplate. Across the world, in laboratories that would not exist for another 73,000 years, scientists would eventually try to answer that question. What they found would not make the story simpler. It would make it more honest. And honest, it turns out, is more interesting than simple. In 1998, a researcher named Stanley Ambrose published a paper that asked a question so direct and so uncomfortable that it has been generating argument ever since. The question was not new. The genetic data that made it possible to ask had been accumulating for years, and other researchers had been circling around its implications. But Ambrose asked it directly, and the answer he proposed was stark enough that the scientific community could not set it aside and move on. The question was, what if Toba nearly ended us? Not ended our civilization, which did not yet exist. Not ended our dominance, which was not yet established. Ended us, the species, the lineage, the particular experiment in primate cognition and social complexity that had been running for 300,000 years and had not yet produced anything that would allow a future observer to recognize it as the beginning of something consequential. His argument rested on the convergence of two lines of evidence that, taken separately, were each significant. Taken together, they pointed somewhere that made a lot of people uncomfortable. The first line was the genetic signal we have already discussed. Human genetic diversity is unusually low for a species of our age and distribution. The signal in our genomes is consistent with a population that passed through a severe bottleneck at some point in the past. A period during which the number of breeding individuals was small enough and the duration long enough that much of the variation that had accumulated over hundreds of thousands of years was lost. The second line was the timing. The volcanic eruption at Toba occurred approximately 74,000 years ago. Various methods of dating the genetic bottleneck, including comparisons of mutation rates across different regions of the human genome, had produced estimates placing a major population reduction in approximately the same period. The overlap was not perfect. It was not the kind of clean correspondence that closes a case, but it was suggestive in ways that demanded engagement. Ambrose proposed that the Toba eruption caused, or at minimum, severely deepened, the human population bottleneck. And he proposed an estimate for how severe the bottleneck was. The effective population of breeding humans in the aftermath of Toba may have been reduced to somewhere between 10,000 and a few thousand individuals. Some formulations of the hypothesis went lower than that. Sit with that number for a moment, because it requires translation before it means anything. 10,000 people across the entire planet, every human being alive, every potential ancestor of every person who would ever live, gathered into a group that would fit comfortably in a medium-sized concert venue, and the portion of that loop that was actually reproducing successfully, the subset whose genetic contribution would survive into future generations, may have been smaller still. The Toba catastrophe hypothesis, as it came to be called, was not a fringe idea. It was taken seriously by serious researchers, engaged with in serious journals, and it generated a body of scientific literature that continues to grow. For a period in the late 1990s and early 2000s, it represented something close to a working consensus among a significant portion of the researchers studying human prehistory. And then the complications arrived. They arrived, as complications in science usually do, not in the form of a single decisive refutation, but in the form of accumulating evidence that did not fit the clean version of the story. The first complication came from southern India. At a site called Jwalapuram in the Kurnool district of Andhra Pradesh, archaeologists, excavating in the early 2000s, found something unexpected. The white layer of Toba ash was there, unmistakable, its chemistry confirming its origin in the Sumatra eruption. And above the ash layer, and below it, were stone tools, human artifacts, evidence of people making things before the eruption and people making things after it, in the same place, with tool traditions similar enough that the researchers proposed the possibility of cultural continuity across the event. If that interpretation is correct, it means that people survived the Toba eruption in South Asia. Not just survived in the sense of the species persisting somewhere on the planet, survived in the specific region that received the heaviest ashfall outside of Sumatra itself, survived and continued making tools in ways consistent with what they had been doing before. The debate over what those tools actually mean has not been resolved. Some researchers argue that the similarity of the tools above and below the ash reflects recolonization by a different group rather than survival of the same population. Others maintain that the cultural continuity is real. The conversation is ongoing and genuinely unresolved, which means that anyone presenting it as settled in either direction is getting ahead of the evidence. The second complication came from South Africa. The site at Pinnacle Point, which has already appeared in this story as one of the coastal refugia where human occupation appears to have continued through the period of the eruption, presented a record that did not show the gap that a near-extinction event might be expected to produce. People were there before Toba, and people were there after it. The coastal resources that Pinnacle Point provided appear to have buffered the local population against the worst effects of the volcanic winter in ways that made the Pinnacle Point record look different from what the catastrophe hypothesis predicted for global human populations. The third complication came from genetics itself. As the tools available for analyzing ancient and modern DNA became more powerful in the 2000s and 2010s, researchers were able to examine the timing and structure of the human bottleneck with greater precision. What they found was not a simple story. Some analyses supported a bottleneck consistent with the Toba timeframe. Others found evidence of population reductions that predated Toba by tens of thousands of years, or that involved multiple episodes of contraction and recovery rather than a single sharp event, or whose timing did not align cleanly with 74,000 years ago. The relationship between the genetic signal and the volcanic event, in other words, is not the clean one-to-one correspondence that the original version of the hypothesis implied. The genome carries a record of something severe. Whether that something is specifically and exclusively the consequence of the Toba eruption remains genuinely contested. And then there is a fourth complication, perhaps the most important for what it tells us about the limits of confident reconstruction. Research from sites in Malawi in East Africa has produced evidence of significant human activity in the region during and around the period of the Toba eruption. Research from other parts of sub-Saharan Africa has similarly complicated the picture of a uniform global depopulation. The African continent, which is the largest and most geographically diverse landmass in the range of human habitation at this time, does not present a record consistent with continent-wide population collapse. Some regions show evidence of continuity. Others show evidence of disruption. The picture is one of extreme regional variation, not uniform catastrophe. This brings us to the three-layer verdict that the current state of evidence supports, and to the reason why that verdict, honestly delivered, is more interesting than any simpler version of the story. The first layer, the human population, experienced a significant bottleneck, meaning a severe reduction in genetic diversity consistent with a period during which the number of breeding individuals was very small. At some point in our evolutionary past, this is not seriously contested. The genetic evidence for it is robust and has been reproduced across multiple independent analyses using different methodologies. The second layer, the Toba eruption, is a compelling candidate for at least partial responsibility for this bottleneck. The timing is approximately consistent. The magnitude of the eruption was sufficient to cause the kind of global climate disruption that could drive population reduction across a wide range. The evidence of regional impact, particularly in South Asia, is real and significant. The third layer, whether Toba was the exclusive cause, the primary cause, or one of several contributing factors to the bottleneck, remains an open question. The evidence does not currently support closing the case in either direction. Researchers who argue for a strong Toba bottleneck connection and researchers who argue for a weaker or more complicated connection are both working with real evidence and legitimate methodological frameworks. The disagreement is not between science and denial. It is within science, between people trying to extract signal from genuinely difficult data. What this means for the question of how small we were is that we do not have a number we can state with confidence. We have a range of estimates, produced by different analytical approaches, spanning from scenarios in which the human population was reduced to the low, thousands of breeding individuals, to scenarios in which the reduction was severe, but not quite that extreme. We have regional variation that suggests some populations were more affected than others. We have an overall genetic signal that is consistent with something quite serious having happened. And we have an eruption of extraordinary scale that happened at approximately the right time to be responsible. That is the honest account. It is also, if you sit with it properly, one of the most remarkable facts about our species. We carry in our genomes the record of a narrowing so severe that the combined genetic heritage of 8 billion people today reflects the diversity of a group whose size we cannot determine with confidence, but which may have been small enough that their continued existence required a particular kind of luck, or a particular kind of capacity, or both. The question of how small we were matters, but the question underneath it may matter more. If the bottleneck was real, and the evidence says it was, then the people who survived it were not a random sample of the human population that existed before it. Survival at that scale, under those conditions, for that duration, does not select randomly. It selects for something. And understanding what it selected for is, in some ways, more important than knowing the exact number of people who made it through. That is the question we turn to now. Not how many, who, and what about them made the difference. Forget, for a moment, everything that instinct tells you about what makes a creature likely to survive. The instinct is wrong, or rather, it is calibrated to the wrong kind of threat. The instinct says the strong survive, the fast, the fierce, the dominant, the ones at the top of whatever hierarchy the ecosystem has produced, the ones with the largest territories and the most access to resources and the highest social status in whatever social system their species has built. These instincts are not useless. They describe something real about how survival works in stable environments where the relevant pressures are the familiar ones. Competition for food, competition for mates, competition for territory. The pressures that have been shaping the evolution of complex animals for hundreds of millions of years and that have produced, through that shaping, the traits we tend to recognize as survival relevant. The long dark was not that kind of pressure. It was not a competition, in the sense that competition has a winner and a loser, and both parties survive long enough for the outcome to be determined. It was an environmental threshold event, a situation in which the carrying capacity of the landscape dropped below the minimum required to sustain most of the population that was living on it. And the question was not who could outcompete whom, but who happened to have, or happened to be near, or happened to have built across the preceding generations, the specific resources that the specific conditions of a volcanic winter required. The survivors were not, the evidence suggests, the most dominant individuals. They were the ones with the right architecture for a specific kind of catastrophe. Call it survival architecture, because the word architecture captures something important about what it was. It was not a single trait. It was not a single behavior, or a single cognitive capacity, or a single geographical advantage. It was a structure built from multiple components that worked together, that proved more durable under the specific stresses of the long dark than the structures that the pre-Toba world had rewarded. The first component of that architecture was ecological flexibility. The groups whose occupation of the coastal sites shows the most continuity through the Toba period were not dietary specialists. They were not committed to a single food source or a single strategy for obtaining it. The evidence from sites like Pinnacle Point and from other coastal locations of this period shows exploitation of an extraordinary range of resources, multiple species of shellfish harvested at different tidal levels and in different seasons, fish taken by multiple methods, marine mammals, coastal birds, terrestrial plants collected from the hinterland behind the shore, roots and tubers processed by methods that required knowledge to perform safely, insects in seasons when other protein sources were scarce. This is not a simple behavior. Processing shellfish requires knowing which species are safe in which seasons, because some shellfish accumulate toxins during algal blooms that make them dangerous to eat at certain times of year. Exploiting different tidal zones requires knowing the specific timing of tidal cycles and the specific locations where different species concentrate at different phases of the tide. Using marine resources in combination with terrestrial resources requires maintaining knowledge of two entirely different food systems simultaneously, and switching between them as conditions change. This is a cognitive and behavioral repertoire of considerable sophistication, and it is a repertoire that, crucially, does not fail catastrophically when any single component of it fails. When the shellfish in one location become temporarily depleted, you shift to another location or another species or another food category entirely. When the terrestrial plant resources inland contract under the stress of reduced sunlight, you increase your investment in marine resources that are less sensitive to that reduction. The system has redundancy, and redundancy, under catastrophic stress, is the difference between a system that degrades gracefully and a system that collapses. The second component was the social network. We have already encountered the network in the world before Toba, the web of relationships between groups that allowed materials and information to move across distances larger than any single group could span. What the long dark reveals about that network is not simply that it was valuable. It reveals the specific ways in which it was valuable under conditions of severe and prolonged stress. A network carries information, not just information about where food is. Though that is important, information about which routes are still passable when the landscape has been disrupted. Information about which groups are still present and where they are, and whether they have resources to share. Information about conditions in territories that your own group has not visited recently and cannot visit without knowing something about what they will find there. In a world where the environment was failing unevenly, where some coastal refugia were still producing while inland areas were collapsing, where some river systems maintained water while others had dried, the most valuable thing you could possess was not a physical resource. It was a map. Not a literal map, not a drawn or written artifact, but a mental map built from information flowing through a network of relationships. A map that told you where the world was still working and how to get there. The groups whose networks were still functioning in some form through the long dark had access to that map. The groups whose networks had collapsed were navigating without it, making decisions about where to move and how to move based only on what they could directly observe, which in a disrupted landscape was far less than what they needed to know. The evidence for the continuing function of exchange networks through this period is fragmentary but real. Materials that required transport from specific geological sources appear at coastal sites of this period in context suggesting that the supply of those materials did not completely cease during the eruption's aftermath. The network did not function at its pre-Toba level, but it did not disappear entirely, and what remained of it may have been enough to maintain the information flow that made the difference between finding a coastal refugium and not finding one. The third component was intergenerational knowledge transmission. This is the component that leaves the least physical trace in the archaeological record, and that may have been the most important of the three. Every piece of the ecological flexibility described above, every specific technique for processing a particular shellfish species safely, every piece of knowledge about the timing of tidal cycles, every understanding of which plant species are reliable food sources in a drought that extends longer than usual, existed in specific people. It had been put there by other specific people, through a process of deliberate teaching that required time and attention, and a relationship between teacher and learner that was stable enough to allow the transmission to occur. When people died without transmitting what they knew, the knowledge died with them, not temporarily, permanently. The knowledge of how to process a specific food source safely cannot be reinvented from first principles by a person who has never seen it done and has no one to ask. The knowledge of which route through a changed landscape leads to water cannot be discovered without the cost of the journey that discovers it. A cost that a group running on severe caloric deficit cannot always afford to pay. The older members of any group carried decades of accumulated observation. They had seen dry seasons that lasted longer than usual. They had found food in places that younger members of the group did not know to look. They had navigated crises that the younger people had not experienced and had learned from navigating them, things that could not be learned any other way. In the context of the long dark, the survival of older group members was not simply a matter of compassion or social obligation. It was a survival strategy. The group that kept its elders alive was the group that kept its accumulated knowledge alive. And the accumulated knowledge was, in a world where the familiar environment was no longer producing familiar results, the most valuable resource the group possessed. The grandmother hypothesis, a framework that researchers have developed to explain why human females have an extended post-reproductive lifespan unusual among mammals, proposes exactly this kind of mechanism. The knowledge and labor of post-reproductive women. Women who are no longer reproducing themselves, but who remain vigorous enough to contribute to the group's food supply and to the care and teaching of younger members, provides a survival advantage to the lineages they support that shows up in the genetic record as selection for longer lifespan in women. In the conditions of the long dark, this advantage would not have been abstract or long-term. It would have been immediate and specific. The woman who knew where the water was when the usual water sources were compromised, the woman who knew which plant species could be processed safely when the familiar food plants were not producing, the woman who knew, from having lived through previous hard seasons, that this particular kind of difficulty had an end, and that the behavior most likely to reach that end was this specific set of choices rather than some other set. That knowledge was not written anywhere. It was in her, and the group's ability to keep her alive long enough to transmit it, and to transmit it to people present and stable enough to receive it, was one of the things that determined whether the group made it through. The fourth component was the capacity for what cognitive scientists call displaced reference, the ability to communicate about things that are not immediately present, about the past, about the future, about the hypothetical, about the conditions that exist in a place you are not currently in, but that someone in your network has visited and can describe. You cannot maintain a network across distances of hundreds of kilometers without a communication system capable of encoding and transmitting complex information accurately. You cannot transmit knowledge about a food source that is only available in a specific season, or in a specific location you are not currently in, or that requires a preparation process that must be described before it can be demonstrated. Without language capable of referring to things not immediately present, the survivors were talking to each other in ways that made the survival of the group possible. They were describing what they had seen in places they had been. They were planning movements toward resources they had not yet reached. They were transmitting the knowledge of how to do things to people who had not yet done those things. They were, in the most fundamental and consequential sense, sharing what they knew with people who needed to know it. This is not a minor observation. The capacity for displaced reference, for language that can refer to the absent and the future and the hypothetical, is the cognitive foundation of everything that makes human beings different from every other species that has ever existed on this planet. It is the foundation of cumulative culture, of the ability to build on what previous generations knew, rather than starting from the beginning with each generation. It is the foundation of the knowledge transmission that kept the group's accumulated understanding of the world alive through the deaths of the people who had accumulated it. The survivors were not merely using language. They were depending on it in ways that placed an extraordinary premium on its precision and its complexity and its ability to carry meaning accurately across the gap between one person's experience and another person's understanding. What the profile of the survivors describes, assembled from the archaeological evidence and the genetic record and the logic of what the conditions of the long dark required, is not a type of body, not a measure of individual strength or speed or dominance. It is a type of relationship to knowledge and to other people, a way of being embedded in a group that treated what you knew as a resource that belonged to the group, not just to you. A way of maintaining connections to people beyond your immediate family, because those connections carried information and options that no individual or small family could generate alone. A way of passing forward what the group had learned so that the next generation did not have to learn it from the beginning at a cost the group could not afford. Survival architecture, built not in a single generation and not by any individual genius or heroic act, built across generations. Through the patient accumulation of knowledge and the persistent maintenance of relationships and the daily practice of teaching what you knew to the people around you. The woman from the coast had this architecture, not because she was exceptional, because she was embedded in a group that had built it across enough generations that it had become the foundation of how the group functioned. She did not know she was a survivor of a near-extinction event. She knew she was doing what needed to be done to get through another day, and then another day after that. From the outside, across 74,000 years. Those two descriptions are the same thing. Now ask the harder question. If the people who survived the long dark survived because of ecological flexibility and social networks and intergenerational knowledge transmission and the capacity for displaced reference in language, what did the experience of surviving do to those capacities in the population that emerged from the bottleneck? What does a severe population reduction, followed by recovery from a small founding group, do to the traits that characterized that founding group? And is there anything in the 74,000 years that followed, anything in what our species built and how we built it and what we are still building today, that suggests the answer to those questions might matter? That is where we go next. And the honest answer is, we do not know for certain. But we can look at what the evidence allows us to say. And what it allows us to say is more interesting than certainty would have been. The survivors were not random. The traits that kept them alive were specific. And when you look at what those traits produced across the 74,000 years that followed, when you look at what our species has built and what it continues to build and what it reaches for, even in its most difficult moments, you begin to wonder whether Toba did not just test the human lineage, whether it may have, in ways that science is only beginning to find the tools to examine, shaped it. The question is speculative, but speculation, held honestly and labeled clearly, is not the same as ignorance. It is the beginning of understanding. There is a version of this story that ends here. The bottleneck happened. The survivors survived. The population recovered. 74,000 years passed. 8 billion people exist. End of story. That version is true. It is also, if you have been paying attention to what the evidence actually shows about who survived and why, unsatisfying in a specific way. It stops at the moment when the most interesting question is just becoming visible. The question is this: if the people who made it through the long dark were not a random sample of the pre-Toba human population, if they were disproportionately the ones with particular kinds of social architecture and particular kinds of cognitive flexibility and particular kinds of investment in knowledge transmission, then what did the process of selection do to those traits in the population that recovered from the bottleneck? This is where honesty about what the evidence allows requires a clear label on what follows. What follows is speculative, not irresponsibly speculative. Not speculation that ignores the evidence or invents connections that have no basis in what we know. But speculative, in the technical sense, it goes beyond what the current evidence can confirm and into the territory of what the evidence, combined with what we understand about evolutionary and cultural processes, makes plausible. Every claim in this section should be heard with that label attached, not because the ideas are not worth taking seriously, because taking them seriously requires being honest about what kind of ideas they are. With that said, here is what survival may have left behind. Begin with the simplest version of the argument, the one that requires the fewest assumptions. When a population passes through a severe bottleneck and then recovers, the traits that characterize the surviving group are disproportionately represented in the recovered population. This is not a controversial claim. It is a straightforward consequence of how genetic inheritance works, applied to behavioral and cognitive traits as much as to physical ones. If the surviving group was disproportionately composed of individuals with strong social networks and high behavioral flexibility and sophisticated knowledge transmission systems, then the population that recovered from the bottleneck would have been, on average, more concentrated in those traits than the pre-bottleneck population. This is natural selection operating on a timescale and through a mechanism that does not require generations of gradual change. A bottleneck can do in one catastrophic episode what ordinary selection does across thousands of generations. It can concentrate traits by removing the individuals and lineages that do not carry them in sufficient degree to survive, the specific conditions of the filtering event. Whether Toba produced this effect in any measurable way on the human genome or on human behavioral tendencies is something that current science cannot confirm. The tools for detecting behavioral selection in ancient populations from genetic data are still being developed, and the uncertainties involved in using modern behavioral data to infer anything about the traits of populations 74,000 years ago are substantial. This needs to be said clearly and early. But the logic of the mechanism is sound, and there are three areas where the logic, combined with what we observe about our species, produces ideas that may be worth holding carefully. The first is language. Complex language, the kind that can refer to things not immediately present, that can carry meaning accurately across the gap between one person's experience and another's understanding, that can encode and transmit knowledge about the past and plans for the future and warnings about things not yet encountered, did not originate with Toba. Some form of complex communication was present in our lineage well before 74,000 years ago, as the evidence of symbolic behavior and long-distance exchange at sites predating the eruption makes clear. But language is not a binary. It does not simply exist or not exist. It exists on a continuum of complexity and precision and expressive range, and the conditions that favor movement along that continuum are conditions that place an extraordinary premium on accurate communication. A small group of people living through years of compounding scarcity, dependent on coordinated behavior for survival, maintaining connections across distances that required explicit communication to sustain, carrying knowledge that existed only in people and that could only be transmitted through careful teaching, would have experienced selection pressure for more precise and more elaborate communication in ways that a large, widely distributed population with abundant resources would not. When knowledge is plentiful and easily reacquired, the cost of imprecise communication is low. When a single piece of knowledge, the location of a water source, the preparation method for a borderline toxic food, The route through a disrupted landscape is the difference between a group that makes it through the next month and one that does not. The premium on saying exactly what you mean and understanding exactly what someone else means becomes very high. The bottleneck may have been, among other things, a pressure system for the elaboration of linguistic complexity, not because scarcity makes creatures smarter, because the specific social and survival conditions that the bottleneck created, small groups, high interdependence, irreplaceable knowledge that could only be preserved by transmission, placed a higher value on communicative precision than the pre-bottleneck world had placed on it. This is speculative. The mechanism is plausible. The evidence that it actually occurred in this way does not yet exist in the form that would allow it to be stated as fact. The second area is what cognitive scientists call theory of mind. Theory of mind is the capacity to model the mental states of other individuals, to understand that other people have beliefs and intentions and knowledge that are different from your own, to use that understanding to predict how they will behave, to communicate in ways that take their perspective into account, to cooperate with them toward goals that neither of you can reach alone. It is, among other things, the cognitive foundation of teaching. You cannot teach effectively without a model of what the learner knows and does not know. Without the ability to identify the gap between your understanding and theirs, and to construct communication that bridges it. Teaching is applied theory of mind, and the transmission of knowledge across generations that characterize the survival architecture of the bottleneck survivors was, at its core, a teaching enterprise. The conditions of the long dark would have placed an extraordinary premium on exactly this capacity. Reading the intentions of other group members accurately enough to trust them with scarce resources. Managing relationships within a small group under severe stress without allowing conflict that the group could not survive. Understanding how to communicate with members of other groups, people whose immediate experience and knowledge base differed from your own, in ways that sustained the network rather than disrupting it. These capacities may have been present in our lineage before Toba. They may have been sharpened by the specific conditions the bottleneck created. They may have been disproportionately represented in the surviving group in ways that made the recovered population somewhat different from the population that entered the dark. Or none of this may have happened in any way that left a detectable trace. The honest answer is that we do not know. What we can say is that we are, as a species, of remarkable social sophistication. Our capacity for modeling each other's intentions, for coordinating behavior across large groups of individuals with no personal relationship, for building and maintaining the shared systems of meaning that make complex societies possible, is without parallel in the animal kingdom. Whether the bottleneck shaped that capacity or simply tested it and found it already present is a question the current evidence cannot resolve. The third area is the one that requires the most care, because it is the one most easily misread as a stronger claim than it actually is. It is the question of what the bottleneck means for the relationship between every human being alive today. The genetic evidence indicates that all living humans are descended from a population that was, at some point, in the period around 70,000 to 100,000 years ago, very small. The precise size of that population, as we have established, is debated. The consequence of that small founding population is not debated. It is visible and measurable in our genomes. It means that the genetic distance between any two humans chosen at random from anywhere on the planet is smaller than the genetic distance between two chimpanzees chosen at random from the same forest. It means that the surface differences between human populations, the differences of appearance and language and culture and history that can feel so fundamental from the inside of any particular human experience, are built on a genetic foundation of extraordinary shallowness and similarity. We are all very recent descendants of a very small group of people. The stranger on the other side of the planet whose life you will never intersect with is, in a biological sense, more literal than the word usually implies. Your relative. Not in the way that all living things are technically related, through the deep history of evolution, in the way that cousins are related, in the way that people who share recent common ancestors are related, ancestors recent enough that the genetic signature of that shared ancestry is still visible in both of your genomes. Toba did not create this unity. The unity preceded the eruption. But the bottleneck, if it occurred in the way the evidence suggests, compressed it. It drew the thread of our common ancestry tight enough that the family resemblance between all living humans goes deeper than any surface difference. Deeper than language and culture and geography. All the way down to the level of the molecule. This is what the bottleneck may have left behind. Beyond any specific cognitive or behavioral trait. A species whose diversity, real and valuable as it is built on a foundation of profound genetic similarity. A species that is, whatever the appearances suggest, one extended family navigating a very large planet. Whether that fact changes anything about how we treat each other is a question that biology cannot answer. But it is a fact, and facts, honestly held, have a way of mattering eventually. Here is a question worth sitting with. What would it take for an event of Toba's scale to happen again? The answer is nothing exceptional. Nothing that requires any unusual alignment of geological forces or any departure from the ordinary operating conditions of a planet with active tectonics and a partially molten interior. What it would take is exactly what it took 74,000 years ago, a magma chamber filling incrementally over a very long time until the pressure exceeds the strength of the rock above it. That process is underway right now, in multiple locations on the surface of this planet, in the same ordinary and patient way that it has always been underway. This is not a prediction. It is not an argument that a Toba-scale eruption is imminent or likely on any time scale that matters to the people alive today. What it is a statement about the category of event that Toba represents, and about the relationship between that category and the civilization that currently occupies the planet where that category of event occurs. Begin with the systems that researchers are currently monitoring. Yellowstone, in the northwestern corner of the continental United States, sits above one of the most studied volcanic hotspots on Earth. The hotspot has produced 3 major caldera-forming eruptions in the past 2.1 million years. The most recent of those eruptions occurred approximately 640,000 years ago and produced an event estimated at roughly 1,000 cubic kilometers of ejected material. Smaller than Toba, but in the same order of magnitude of geological consequence. The popular framing of Yellowstone as a threat that is somehow overdue, based on dividing the time since the last eruption by the average interval between the previous ones, reflects a misunderstanding of how volcanic systems work that the United States Geological Survey has corrected publicly and repeatedly. Volcanic systems do not operate on schedules. The interval between past eruptions does not predict the timing of the next one. The magma system beneath Yellowstone is real. It is being monitored continuously with instruments of extraordinary sensitivity, and it is currently showing no evidence of unusual activity that would suggest an eruption is approaching on any human-relevant timescale. What the monitoring shows is a system that is dynamic and active in ways consistent with its geological nature, producing earthquakes and hydrothermal activity as it always has, without the specific signatures that would indicate movement toward a large eruption event. The scientists who monitor Yellowstone are not, as some popular treatments of the subject imply, sitting on alarming data that they are choosing not to share. They are monitoring a geological system of extraordinary interest and publishing what they find, which is that Yellowstone is active and not currently threatening. The reason the monitoring matters is not that a Yellowstone eruption is expected. It is that the consequences of a large eruption would be significant enough that any warning, however limited, would be valuable. An early signal, even one that provided only months of notice, would allow responses that no warning at all would not allow. The monitoring is an investment in the value of information. Made on behalf of a population that would be affected by the event it is designed to detect. In southern Italy, the situation at the volcanic system called Campi Flegrei is more immediately active and more immediately discussed among the researchers who study it. Campi Flegrei is a caldera system located just west of Naples, a city of nearly 1 million people, within one of the most densely populated regions of southern Europe. The system last produced a major eruption approximately 39,000 years ago, and a smaller but significant eruption in the year 1538, in the decades preceding the present. Ground within the Campi Flegrei caldera has been rising, a process that indicates movement of magma or hydrothermal fluids within the system below. The rising ground has been measured, documented, and studied with the full range of modern volcanological tools. Researchers disagree about what it means for the probability and potential scale of future activity. What is not in dispute is that the system is active, that it is located beneath a significant and dense human population, and that any eruption of significant scale would require the rapid evacuation of hundreds of thousands of people from a region with the infrastructure complexity of modern southern Italy. Campi Flegrei is not Toba. Its maximum potential eruption is estimated at a scale considerably smaller than the great supervolcanic events of the past 2 million years. What it represents in this context is not a threat equivalent to Toba, but a reminder that the category of events capable of causing severe regional disruption is not confined to the geological deep past. It is present, it is being monitored, and it is unresolved. Beyond these two most discussed systems, the global inventory of potentially active supervolcanic systems includes sites in New Zealand, in Indonesia, in Japan, and in other geologically active regions. None of these systems are currently presenting evidence of imminent, large-scale activity. All of them are real. All of them are being observed with varying levels of instrumentation and scientific attention. Now ask a different question. If a Toba-scale eruption occurred today, what would it encounter? It would encounter a global civilization of 8 billion people. A civilization whose food production system feeds those 8 billion through a network of agricultural systems that are, by any historical standard, extraordinarily efficient and, by any resilient standard, extraordinarily specialized. Modern industrial agriculture produces more food per unit of land than any previous food production system in human history. It does this through a combination of high-yield crop varieties, synthetic fertilizers, irrigation infrastructure, mechanized production, and global supply chains that move food from regions of surplus to regions of deficit with a speed and volume that would have been incomprehensible to any previous generation. Every one of those mechanisms is calibrated to the climate conditions that currently exist. The crop varieties that produce maximum yield under current temperature and precipitation regimes may produce substantially less under a volcanic winter regime. The irrigation systems that deliver water to fields in currently semi-arid regions depend on precipitation patterns that a large eruption would disrupt. The supply chains that distribute food globally depend on the same transportation, infrastructure, and economic systems that every other disruption also stresses simultaneously. The efficiency of the modern food system is real, but efficiency and resilience are not the same thing. A system optimized for maximum output under a specific set of conditions is not necessarily a system capable of maintaining adequate output when those conditions change rapidly and severely. The hunter-gatherer groups of 74,000 years ago were, by efficiency standards, far less productive than a modern agricultural system. But their flexibility, their ability to shift strategies and food sources and locations in response to changed conditions, gave them a resilience that industrial monoculture does not possess in the same form. This is not an argument for abandoning modern agriculture or for pessimism about human adaptive capacity. It is an observation about where the vulnerabilities lie in the systems that currently sustain 8 billion people, and about why a category of event that human civilization has never experienced at full scale deserves more serious attention than it typically receives. The gap is not in our scientific capacity to understand these risks. The scientific community studying supervolcanic systems is serious, capable, and producing work of genuine value. The gap is in the cultural and institutional capacity to take seriously a category of risk that operates on timescales longer than electoral cycles, longer than the planning horizons of most governments and corporations, longer than the attention spans that the current information environment tends to support. Low probability, high impact events are precisely the category of risk that human cognitive architecture handles worst. We are very good at responding to threats that are immediate and visible and comparable to threats we have encountered before. We are much less good at allocating sustained attention and resources to threats that are distant in time, invisible in their current form, and without precedent in the range of experience that any living person can draw on. This is not a new observation. Researchers in risk communication and decision science have been making it for decades. What Toba adds to it is a reminder that the category of event we are discussing is not theoretical. It happened. It happened to our species, at a time when our species was small and vulnerable enough that the event may have come close to ending the story before it had properly begun. The fact that we are here to discuss it is not evidence that events of this scale are harmless. It is evidence that our ancestors, in their smallness and their vulnerability, happened to have enough of the right things in the right places to survive. We are larger now. We have more resources and more knowledge and more capacity for coordinated response than any group of humans that has ever existed. We also have more to lose, and we have built our systems in ways that assume the stability of conditions that a large volcanic eruption would not leave stable. The survivors of Toba did not choose their test. They did not know they were being tested. They responded to the conditions in front of them with the best tools they had, and some of them survived. And we are descended from those who did. We have better tools. We know more about what the tests look like before they arrive. What we do with that knowledge is, unlike almost everything else in this story, genuinely a matter of choice. The choice is ours to make, and the time to make it is not when the ground begins to shake. The lake is still there. Toba, in the highlands of northern Sumatra, is one of the most beautiful places on the surface of this planet. The water is clear and deep, filling the caldera that the eruption left behind with a stillness that gives no indication of what formed it. The hills around it are green with tropical vegetation that has had 74,000 years to return. The birds that call from the forest edge around the lake have no awareness that they are calling from the rim of the largest volcanic disaster in the recent history of the planet. The fishermen, who take their boats out onto the water in the early morning, have no sensation of crossing something that was once the floor of a catastrophe. The place looks like what it is, which is a lake. It does not look like what it also is, which is a scar. In the years after the long dark began to lift, in the period when the aerosol layer was thinning and the light was returning and the ecosystems of a damaged world were beginning, slowly and unevenly, to rebuild themselves, something was happening in the small groups of humans who had made it through. Children were being born, not in the numbers that had existed before the eruption. The population that remained was too small and too scattered for rapid recovery. But children were being born in the coastal refugia where the thread had held most firmly, in the river valleys where permanent water had sustained small groups through years when other water sources had failed, in the places where the combination of geography and knowledge and maintained connection had proved just sufficient to keep people alive through seasons that were not designed to be survived. Some of those children lived, and some of those who lived grew up and had children of their own. And the thread that had been drawn so thin that the question of whether it would hold was not rhetorical began, incrementally, and without any announcement that anyone present could have recognized as significant, to thicken. We do not know what those years felt like from the inside. We know what the outside evidence shows: continuous occupation at some sites, the persistence of some form of the exchange network in some regions, the gradual elaboration of behavioral complexity that the archaeological record captures in its incomplete and fragmentary way. We know that the recovery happened because we are here. We do not know, and cannot recover, what it cost the people who lived through it, what they lost that was not recovered, what knowledge died with the people who held it and was never reconstructed because there was no one left who had received it before those people died, what connections were severed and not re-established, what versions of human experience ended quietly, not with a dramatic death, but with the death of the last person who remembered them. We know only that they continued, that the woman from the coast and the people around her and the people connected to them across the distances of a world that was damaged but not entirely broken, kept making the small decisions that survival required, kept moving toward food and water, kept teaching what they knew to the people who did not yet know it, kept maintaining, against the pressure of everything that was working against maintenance, the relationships that made individual survival into something more durable than individual survival alone. Somewhere, in a place we cannot locate and at a moment we cannot date, a child was born who would become an ancestor of every person alive today. Not the only child born in that period, not a special child in any way that anyone present could have identified, a child who happened to survive, and whose descendants happened to survive across the generations that followed, until the chain of survival reached a length of 74,000 years and a breadth of 8 billion people. The genetics tell us this is not metaphor, it is biology. Every person alive today traces their ancestry through pathways that diverge and reconverge across 74,000 years of human history, to the small group of people who came through the long, dark, the apparent diversity of human populations, real and significant, as it is at the level of culture and language and history and lived experience, is built on a foundation of genetic similarity that reflects how narrow the passage was that we all came through. The person whose politics make you certain you have nothing in common with them carries in their genome the signature of the same bottleneck you carry in yours. The child born this moment on the other side of the world is your relative in a sense more literal than the word usually implies. The strangers you will never meet, living lives you cannot imagine, are members of the same extended family that you are a member of, separated by 74,000 years of divergent experience and united by something older and more fundamental than any of those divergences. They are here because the thread held. Think about what that means for a moment. Not as a scientific conclusion to be filed and moved past, as a weight you can actually feel. Every teacher who taught what they knew to someone who needed to know it, every elder who stayed alive long enough to pass forward the knowledge that decades of living had given them, every person who maintained a connection to people beyond their immediate circle when maintaining it was costly and the return was uncertain. Every group that kept its network functioning when the network was stressed, past the point where functioning seemed reasonable. All of it traces back, through an unbroken chain of choices made by people who did not know the choices were significant, to the people who survived the long dark by doing exactly those things. The debt we carry to those people is not a debt that can be repaid in any direct sense. They are beyond reach. What they did without knowing they were doing it for us. They did it because it was what survival required, and because the capacity to do it had been built into them across generations that preceded even them. What we can do, and what the evidence of the long dark suggests we are built to do, is the same thing they did. Share what we know. Maintain the connections that carry information to people who need it. Keep alive the knowledge that exists only in people, by finding the people who hold it and creating the conditions under which they can transmit it. Build the networks that give any individual access to more than any individual can generate alone. These are not abstract virtues. They are the specific behaviors that kept the human lineage alive through the worst conditions it has ever faced. They are encoded in our history in ways that our genome still reflects. And they are, as it happens, also the specific behaviors that our current moment most requires. The survivors of Toba did not know they were survivors. They did not know that the difficulty they were living through had a name or a cause or a scale that would one day be measured in cubic kilometers and ice core data and the low genetic diversity of 8 billion people. They knew that morning came again. They knew that the work in front of them was the same work it had always been. Find food. Maintain relationships. Teach what you know to the people around you. Keep going. They kept going. Here, 74,000 years later, is what keeping going produced. A world of 8 billion people, all of them related, all of them descended from a group small enough that we still carry the genetic signature of how close the call was. All of them, the inheritors of a capacity for social complexity and knowledge, transmission and communicative precision that may have been forged, or at minimum preserved, by the worst years our species has ever endured. The sky above Toba this morning is blue, clear, full of light that reaches the surface without filtration, without the scatter of a stratospheric aerosol layer, without the particular quality of wrongness that the woman on the coast spent years learning to live with without ever being able to name. Just light, the ordinary, irreplaceable light of a morning that is not the end of anything. We are alive in that light because of people who kept going, when going was the hardest thing available to do. The least we owe them is to understand what they did, and to recognize when the choices get hard and the connections get costly, and the knowledge that needs to be passed forward requires more effort to transmit than it seems worth, that this is exactly what they were doing, in the dark, without knowing if it would be enough, without any guarantee except the one that survival has always run on, that continuing is better than not continuing. And that what you do with the time you have is the only answer the question of survival has ever accepted.